right, so we're still in 1.4. We're still going to be talking about limits and continuity. All right, put them out. What's a limit? When you do what? Approach from both sides arbitrarily close to a number, a y-value number. Now, we talked about continuous. Layman's term for continuous, you can do what?
Keep your pencil down.
Keep your pencil down. You can draw without letting your pencil. Keep that pencil down. All right? Mathematically, the limit as x approaches c of f of x is equal to the value f of c. This is definition continuity mathematically, and that's where we're going to be spending our time. All right? Keep that pencil down. All right? So I kind of want to look at like numbers 3 or 4 from your homework last night. When we did number 3 or 4, if we say, let's look at just number 3. The limit as x approaches 3 of this function on number 3 was 0. However, what was f of 3 on the homework last night? Look at the picture. What was the value f of 3? 1. Now, did it have a limit? Yeah, sure did. However, it wasn't a continuous function because it was a removable discontinuity. All right? Because the limit was not equal to the value. Does that make sense?
Yeah.
All right? Mathematically, that's what we're talking about. Now, when we're talking about endpoints, technically we can't have a limit at an endpoint. Because why? I can't come from both sides, exactly. So if we have a limit for like this endpoint A, we have to approach it from which way? The right, you have to. And then point B, it would have to be from the what? The left. But does the limit as x approaches A actually exist? No. All right, we have to have a one-sided limit to take care of it. So here we go. Let's talk about these one-sided limits. Write this one out. Limit as x approaches -2 from the right of square root 4 minus x squared. Now, this was on our summer coursework. This is something that you have to recognize. What kind of function is this square root 4 minus x squared thing? It's a semicircle, exactly. And what's my radius of this guy? 2. Okay, so it should look like that. All right, you have to be able to recognize that, not only for limits, but once we get into chapter 4 and we start taking integrals, we have to understand that. All right, so if I do a limit as x approaches -2 from the right, well, what y value does it go to? It's not a trick question. It goes to 0. Exactly. Now, if I didn't understand the graph, if I said the limit as x approaches -2 of square root 4 minus x squared, what do I try to do first every single time? I try to direct substitute. Could I direct substitute -2 in? Yeah, it'd work. And what would I get? I'd get 0. However, is my limit as x approaches -2 0? No. What is it? It doesn't exist. All right? Because it's actually at the end point. I can't go from the left. All right? So that's something that we have to be aware of on what it's doing. All right? All right, we're moving. This is what's called a greatest integer function. Remember these from pre-calc a little bit? Our step functions or our greatest integer functions. It's kind of what's in between it and the step that it's still on and it hasn't reached the other one. Same kind of stuff, but now we're going to put limits on it. It's basically the same thing. So let's start out with this 5.1 thing. What is the greatest integer of 5.1? What is 5.1 in between? And please go in order.
5 and 6.
5 and 6. Has it gotten to 6 yet?
No.
No. So what step is it still on?
5.
It's still on step 5. Now, let's do the greatest integer of -2.6. Well, what's it in between? And please go in order. -3 and -2. Has it gotten to -2 yet? No. So it's still on what? Step -3. Now we're going to put limits into practice here. All right. So now I take a limit as x approaches 0 from the right of the greatest integer function of x. All right. So that means it's just a little bit more than 0. You following me? If it's from the right, it's just a little bit more. It's the positive part of 0. So what step would that be on?
0.
It would be on 0. However, if I do a limit as x approaches 0 from the left of my greatest integer, that's just a little bit negative of 0, a little less than 0. What would that step be on?
-1.
That would be on -1. However, what if I were asked, what's the limit as x approaches 0 of my greatest integer x? What would that answer be?
0.
Huh? It's a jump. Does not exist because it's a jump. All right? Because what's a limit? When you do what? When we approach from both sides. If I approach it from the left, it's -1. If I approach it from the right, it's 0. All right? It does not match up. So we have a special high five and jump discontinuity. All right? All right, let's pick some numbers. Katie did. Pick me a number.
6.
6. The limit as x approaches 6 from the right. All right, so I'm a little bit positive of 6. So where am I?
6.
I'm at 6. All right. Harshna, pick a negative number.
-4.
-4. So I'm taking a limit as x approaches -4, and I'm going to say the left. All right. So I'm going to say x approaches -4 from the left of my greatest integer function. So what would that be?
-5.
That would be -5. Okay, because it's a little bit negative of -4. All right. So that would end up being -5. All right, pretty good on greatest integers?
Yep.
Okay. All right, so again, for a limit to exist, it has to go what? From both sides. For it to be continuous, the limit has to equal the value. All right. In layman's terms, what?
Keep the pencil down.
Keep the pencil down. My man. All right, so now we're going to talk about continuous functions. It's continuous on every point on that interval. Now, let's look at this function right here. I got 1 over x. Is that a continuous function?
No.
I say yes.
I think yes.
Where is it not continuous?
0.
It's not continuous at 0. But what if I said I want the interval 2 to 5? Would that be continuous?
Yeah.
Yes. It depends what interval you're talking about. All right. So if I say the interval 0 to infinity, would that be continuous?
Yep.
Yes. However, what if I said the interval -1 to 1? Now would that function be continuous? No, because where does it break?
0.
It breaks at 0. All right. So for instance, let's deal with another one. Let's just say, like, I don't know, f of x is equal to 1 over x plus 3. Do I have a continuous function on, let's say, -1 to 5?
Yes.
Is it continuous on that?
Yes.
Sure is. But is it continuous on, let's say, -5 to -1?
No.
No, it wouldn't be continuous there. Why?
Breaks something to -3.
It breaks at -3. All right. So a function might not be continuous everywhere, but on these certain intervals that you want it, it will be fine. Okay. It just can't break on that interval that you're talking about. Does that make sense?
Yeah.
All right. Write out number 63. So we're going to solve for our constants so that we can make this a continuous function. So what we're really trying to get at is the limit as x approaches c of f of x is equal to my value f of c. That's what we're trying to get at. All right. Well, what's a limit? When you do what? When you approach from both sides. So where's my problem area look like it might be on number 63? 1. All right. So I need to take a limit from the left of 1. And I need to take a limit from the right of 1. Well, if I do a limit from the left, am I looking at the top or the bottom part? Bottom part. I'm looking at the bottom part. So all I do is substitute in 1 for x. So what do I get? Huh? A minus 4. That's all I get. And then if I substitute in 1 from the right, that top part would end up being what? 3. What do I want to do with those two things? You're funny today. So I set them equal. All right. And so what do I get? A equals 7. All right. And so I have kind of finished my problem. All right. Now, technically, I just found the limits will equal each other. To be continuous, it's a limit is equal to the value. Here's my caution for you. They didn't trick you on this one, but they could. You see how this is x is greater than or equal to 1 and x is less than 1? This would work the same on what we did if it just said x is greater than 1. I'd get a is equal to 7. However, would it be a continuous function anymore?
No.
No, because why?
We don't know what's happening at 1.
It's not filled in at 1. All right? And so it's not dark dot. Yeah. So anyway, be cautious of that. They could trick you. All right? Let's keep moving. So here's another piecewise function. And I need to make sure that it's continuous everywhere. Well, before we had a problem area at 1. Where does it look our problem area is going to be now? -2 and 3. How rude. All right, so we're going to have to kind of do it twice. Well, let's deal with -2 first. So I need to find a limit as x approaches -2 from the left. And I need to take a limit as x approaches -2 from the right. Well, from the left, what would I end up getting? I substitute in -2. What do I get? 7
minus 2 plus 2k.
7 plus 2k. All right. All we did was substitute in -2 into that top equation. And then I need to do -2 from the right. So what do I get there? I substitute -2 in right here. What do I get? -7. All right. So now, what do I want to do with those two statements? Set them equal. All right, so now I have 7 plus 2k is equal to -7. So what does k equal? No.
Oh, negative 7.
-7.
Ah, that actually makes sense.
Well, good. Good. All right. All right, now we need to do limits of what?
It says
3.
if you do that, then it'll make 2k equals -14.
All right. So now we're going to do 3 from the left. And then we're going to do a limit as x approaches 3 from the right. So when I do 3 from the left, what would I end up getting?
-9. Wait, no.
No,
3.
3. All right. And then 3 from the right, what would I end up getting? Three minus 2m. All right.
And it's the one that equals 0.
And so we're going to set them equal. So now what do we get for m, Joseph? 0. All right, m equals 0. All right, so k would equal -7 and m would equal 0. All right, pretty good. All right, and there you go. Go ahead and start.